Okay, Assalamualaikum and very good day, class. Today I'm going to cover about the interrupt. So I'll do a little bit of recap. If you have watched my previous video, I've talked a little bit about interrupts. Okay, so as we know that interrupt is the signal that you send to the processor, telling the processor to do other tasks. Or we can say that telling the processor to do other function. Let's say the processor is processing the main function, and then if you assert the interrupt signal, then the processor knows that you want the processor to process another function, which the address will be given in the software part or in the assembly programming language that the programmer have done. Alright, so this is the basic interrupt event sequence. So the first one is the normal processing here, number one, and then as the interrupt occurs, the processor will save the program counter. Program counter is the register that store the current address of the instructions that the processor is processing. So because you want to execute and you want to go into another address, you have to store the current address here so that when you want to get back to the current program here, you know which address to refer to. And then after you have saved it on the stack, then it start to branch to the ISR, which is the interrupt service routine. And then it'll go into the interrupt service routine, take the address and go to the new address and start to execute the ISR. Fetch the instruction from the address and start to execute it. And then after you have done, after the processor have done executing the interrupt service routine, then it will retrieve back the PC from the stack, which is the PC that we have saved in this step number 3, and then retrieve it back and put it back in the program counter and then resume normal processing. Alright, there are a few types of interrupts, and the first one is the direct interrupts. The direct interrupt is you just have to give the interrupt signal and you don't have to give the address because the address already pre-programmed, already being written in the code. So that's why you don't have to provide the address. But there's another type of interrupt where we call it as vector interrupt. As you send the interrupt signal, you also have to provide the processor with the 16-bit address of the first instruction of the your interrupt service routine. This is not really common being used. The one that is commonly used is the direct interrupts. Even the example that being showed in the lab module for the interrupt lab module is the direct interrupt. Alright, and then the other thing is you have to know is there is non-maskable and also there's a maskable interrupt. Non-maskable interrupt is will always, if asserted, will always being handled by the processor. Yeah, that is non-maskable. So that you cannot disable it by hook by crook. If this interrupt is activated or asserted, then the processor will proceed to process the interrupt service routine. And there's another type of interrupt that is maskable. If the interrupt is asserted, it will only interrupt the processor if it is enabled, which is unmasked. So if you unmask it, that means the interrupt is enabled, then it can ask the processor to go and execute the ISR, which is the interrupt service routine. But if it is masked or disabled, if it's high, it won't change anything on the processor because the interrupt is disabled. Okay, and there are also priority. Let's say you have more than one interrupt signal, there must be a priority so that the processor knows which interrupt to process first. This is the table that show the interrupt pins that you have on 80, 85, and also the priority of each interrupt pins. As we can see here, trap interrupt pin is the highest one, and the lowest one is the INTR interrupt pin. Alright, this is the trigger type. Uh, this is very deep in technical, which is you have to know when is the time that the interrupt is triggered. For example, here trap interrupt, it is triggered at rising edge and also high level. Means that rising edge, if you look at the graph. Okay, wait, let me. Okay, if let's say this is a signal, right? This is your clock signal. Okay, rising edge mean this is a rising edge and also high level. So this interrupt is triggered only when the clock is at the rising edge and also high level. And for this type of interrupt, it has to be enabled at the rising edge of the clock. And for this reset the interrupt pin RST 6.5, RST 5.5, and also INTR, mean it should be high when the clock is high. Yeah, oops. Yeah, this is the when the clock is high, and this is when the clock is low. This is rising edge, and this is the falling edge. All right. All right. Wait, wait. Hmm. Okay, guys. So, okay, this is the example. This is the register. Um, the register inside 8085A, where you can control to enable and disable the maskable interrupts. So this is the maskable interrupts, and this is if you want to change the setting here, you have to enable the mask setting here. We can see from the example that being showed here, this is how you can set the interrupt. For example, we want to enable this to interrupt RST 7.5 and RST 5.5, and we want to disable RST 6.5. So what we should do is that we have to unmask the interrupt that we want to enable. For example, here the 5.5 is here and 7.5. To unmask it, we have to send zero signal. And if we want to disable it, we have to mask it. We have to send one signal. That's what you can see here. And the one signal here, the bit number 4, is to enable the mask settings so that we tell the register that we want to make a change here in the bit here. Yeah. And same goes for the other bits, you can check. And then this is the command that you can use in the assembly language to set the interrupt SIM and also to enable the interrupt EI. All right, this is the example of the main code of your assembly language, where you set all the address for each ISR. For example, here the ISR 5.5 jump to jump start. They are jump to this address 0034H. And if you call the ISR 7.5, you have to go to 003C address. Alright, this is how you set the interrupt first, and then you can this is your regular codes. And if the interrupt is enabled, it will go to this service routine. You have to write your own program inside here, what you want to do inside the interrupt service routine here. After you're done, you have to put this what do you call it, the command here, or the operand return, so that it will return to the main program. Same goes as the ISR 7.5. Okay, what else? Okay, this is the example where we can see the machine cycles with direct interrupt. I mean, this is important class for you to understand the timing diagram. I mean, we call this timing diagram. We can see exactly what is happening each cycle of the clock. As you can see here, this is the clock. I mean, this is the clock that we being provided externally to 8085. For example, it can be 4 megahertz clock, it can be 8 megahertz clock, depend on the specification of 8085A, because you have to check the data sheet what is the clock frequency for 8085A. But the most important thing you have to understand is this is the clock, and all of the instructions, so all of the process that happen inside the processor will be based on the clock. Alright, for example here, this is the direct interrupts. What going to happen if you assert the interrupt signal here? For example here, at this T3 clock cycle, the interrupt RST 7.5 is being asserted and is high here. Then after it being high here, we can see there are 6 cycles here. As you can see, the explanation is here. 8085 processor execute a number of machine cycle in response to vectored interrupt. Oh, sorry, this is vector interrupt. Alright, this is a direct interrupt. Okay, however, to provide the CPU sufficient time to process a direct interrupt, a 60 state bus idle machine cycle is introduced following recognition of the direct interrupt. That's why you see as the interrupt is asserted, there will be 6 cycles here. I mean, this is what happened inside the processor. You have no control of it. I mean, this is already being done by the circuit designer inside the processor. But this is the process that we have to know. I mean, what is happening inside the processor. So after we asserted this interrupt signal, there will be 6 cycles. 60 state bus idle machine cycle is introduced following recognition of the interrupt. So that means the processor acknowledge the interrupt, is already accept the interrupt, and that's why there are 6 cycles here. Alright, and then what else happening? During the bus idle machine cycle, no control signal is asserted, nor is the program counter incremented. Ready line control is ignored during the bus idle cycle. So we call this period is bus idle cycle. No control signal will be accepted. Nothing will happen. And then following the bus idle cycle, 2 memory write cycles are executed to save the current contents of the program counter on the stack. That's why here after we can see after 6 cycles here, what happened is that this is the address of the stack pointer 1, and this is your PC high program counter high. The first sorry the 8-bit, the high 8-bit will be stored in the address of this stack pointer, and then the low 8-bit of your program counter will be stored in the second stack pointer. This is the address for the stack pointer. Yeah, that is basically what happened when the interrupt signal, the direct interrupt signal being asserted on the 8085. So if you guys being asked in the exam to explain about the timing diagram of what is happening if the direct interrupt signal is being asserted, this is the thing that you should explain. All right. Okay, so before I go further, I mean, this is the thing that you have to know. I mean, the ALE I've told last time in the class was the purpose of the ALE signal. So the ALE signals is asserted or is high to tell the processor that the data that they put on this AD0 to AD7 is the address and not the data. Alright, when it's low, then mean is reading this one, the bus AD0 to AD7 bus as a data bus. Okay, what else? Okay, this is the machine cycle with vectored interrupts. Okay, let's this going to be a little bit tedious. Alright, the machine cycle with vectored interrupt. So the 8085 processor executes a number of machine cycles in response to a vectored interrupt prior to execution of the first instruction of the interrupt service routine. The processor completes the execution of the current instruction. The processor only samples the interrupt inputs in the last T state of the last machine cycle in the current instruction cycle. This has implication in system design as it means that the interrupt signal or INTR must remain in the asserted state for at least the longest instruction in 8085A instruction, which is 3 bytes size. Okay, let's see what is meant on the timing diagram. As you can see here class, this is the INTR, your interrupt signal pin. So it should be high at least for 3 clock cycles. Sorry, at least for this as long as this process goes, you can see the interrupt signal has to be high. This is just for vector interrupts. It's different from the direct interrupt where you can see the interrupt signal just high for a while and then it goes down again. But here for the vector interrupt, it should stay at 1 until it finish uh, processing the whole interrupt cycles. Alright, as you can see here, I mean, as the signal is high, I mean, we can see that nothing happened for until T3 because what happened is that the processor will be finishing whatever it is executing until it's done. Then it start to process the interrupt. So as you can see, how we can know that the processor already processed the interrupt because of the signal here, INTA. This is the output signal that being sent from 8085. I mean, this is output signal that is sent out by 8085A processor to tell uh, the whatever output device that it being communicate with that it is processing the interrupt. So what happened here is that it will, okay, let's go to the explanation again. All right. Okay, the processor then executes 60 state interrupt acknowledge machine cycle. It's the same like the direct interrupts is also 60 state. The INTA machine cycle is similar to the opcode fetch machine cycle except that the program counter is not incremented and the INTA control signal is asserted instead of read. So it is also similar like the output fetch. I mean, you can neglect this part, but the most important thing is that you have to know that the processor will execute 60 cycle to acknowledge the interrupt. So in response to the interrupt acknowledge signal, the interrupting device need to place the opcode of an instruction onto the bus called jamming. This is just for the vectored interrupts. So after we know that the processor 8085 already acknowledged the interrupt, we have to use this the opcode. I mean to place the opcode of an instruction onto the data bus. The processor reads the opcode in the normal manner and stores it in the instruction register. The choice of opcode is restricted, so there are only few opcodes that you can use here. It's not that you can use the whatever option that you have in the opcode list. So there are only two opcode that you can use, which is call and also RSTN instruction. So the call instruction is a 3-byte instruction with bytes 2 and 3 being the address of the first instruction of the subroutine. So this is the opcode and there will be another byte here, byte 2 and also byte 3. Byte 1 is your opcode, byte 2 and byte 3 will be the address of the first instruction of the subroutine, which is the ISR. So you have to use this opcode inside the program. So after the interrupt already being acknowledged, we have to send this. The processor have to call this opcode. That's why we can see here. Yeah, after the acknowledge, we can see here the call opcode already being fetched here. So being fetched
uh, and then being sent into the instruction register. Okay, what happened next? Okay, following decoding of the call opcode, so it will take the call opcode and put it in the instruction register, and then decode it. The processor executes a further two interrupt acknowledge machine cycles to fetch the address of the ISR. So after fetching, because you remember, right, the data bus only has 8 bit, so we have to fetch 3 bytes, which is uh, 1 byte is 8 bit, 8 bit, 8 bit, 8 bit, so we have to do the process 3 times. That's why we can see here, I mean, after we fetch the call, and then there's another interrupt acknowledge here, and during the cycle here, we fetch the first byte of the address here, D0 until D7, and then the third time of the acknowledge, we fetch the byte 3, the second byte of the address here. All right. Okay, then let's see what happened. Okay, following it, the process is okay. Further to interrupt acknowledge, further to interrupt no acknowledge, right? So we can see here overall there are 3 interrupt acknowledge, right? One here, 2, and also 3. So during the first interrupt acknowledge, the processor will fetch the call opcode and keep it in the instruction register and decode it. And during the second interrupt acknowledge, it will fetch the first byte of the address here. And then during the third interrupt acknowledge, it will fetch and store the second byte of the address. Okay, then what happened? It is incumbent on the interrupting device to place a low byte of the address of the ISR on the data bus in response of the second control signal. Okay, this is just the explanation of what or the thing that I already explained. Okay, then the execution phase of the call instruction can now take place. The processor firstly execute 2 memory write machine cycles to save the current contents of the program counter on the stack, the address as to where in memory the contents of PC is to be saved. Yeah, then after that it start to execute the interrupt. Okay, so after it already fetched the second address, okay, then it will follow the same step like what happened during the direct interrupt here. So it will store the current program counter content on the stack. Yeah, this is the first part here. As you can see, I mean, this is the address register for stack pointer 1, and will store the high bit of the program counter. And in this cycle here, it will store another byte of the program counter content into the stack pointer address here. Alright, then it start to execute the interrupt. Alright, class, that's all for the interrupt. So I hope you can understand it. You have to go through your lecture note and have to try some labs to get better understanding on the interrupts. Alright, see you again next time. Thank you.